Hello, my name is Peter Newfrick, and I'm the NVMe Technical Workgroup Chair, and I'm going to describe the NVMe 2.0 specifications, which form the next generation of NVMe technology. Before we dive into details of NVMe 2.0, let's first take a look at NVMe Today. Unlike previous storage technologies where there was one technology for servers, another for client, and yet another for mobile, NVMe technology is used across storage applications. We see NVMe technology used today in everything from cell phones and tablets, to client laptops and desktops, all the way to storage arrays and data centers. The table on the right shows the unit growth for NVMe, and you can see that NVMe has grown from an emerging technology in 2016 to a mainstream technology in 2021. In 2021, we expect over 7 million units shipped into enterprise, over 20 million units shipped into cloud applications, and over 350 million units shipped into client applications. The NVMe architecture has been called the new language of storage, since we are now seeing many people design their systems around NVMe technology. Although NVMe has evolved into much more than we ever imagined when we started, our initial goal in creating NVMe was to create a standard interface for PCIe SSDs. We wanted the same experience as one had with hard drives, where you just plug it in and it works. As you can see from the chart on this slide, in 2021, more NVMe SSDs will ship than all other SSD interfaces combined. And the dominance of NVMe is projected to continue to grow. So with that introduction to where NVMe is today, let's take a look at how we got here. We started work on NVMe in 2009. The first spec that was released was the NVMe 1.0 spec, which defined the NVMe storage architecture, command set, and interface for PCIe SSDs. As NVMe adoption grew, we started work in 2014 on extending the NVMe architecture and command set to fabrics beyond PCIe. We published the first NVMe over fabric specification in 2016. When we published the NVMe over fabric spec, we didn't want to disrupt a growing NVMe PCIe ecosystem. So we made minor changes to the NVMe spec, which continued to largely describe PCIe SSDs and describe the architectural extensions necessary for fabrics in an NVMe over fabric specification. Around this time, we also started referring to the NVMe spec as the NVMe Base specification. This achieved our goal of not disrupting the NVMe specification, but created an unnatural partitioning of functionality across specifications. In 2013, we started work on an NVMe management specification since there was no good storage standard for out-of-band management. This resulted in the NVMe Management Interface specification published in 2015. So as a result of all of this, we had three specifications: the NVMe Base specification, the NVMe over fabric specification, and the NVMe Management Interface specification that were all undergoing active development with specifications being released. So with that introduction into NVMe history, let's take a look at where NVMe is headed. As I previously mentioned, our focus was on creating a standard interface for PCIe SSDs. We were focused on the base NVMe architecture and command set. Our goal was to unify PCIe SSDs around a common interface and get the same behavior as one had with hard drives, where you just plug it in and it works. This required getting an in-box driver into all major operating systems. This work ultimately resulted in the NVMe Base specification. As NVMe SSD adoption grew, our focus shifted to scaling the NVMe architecture to fabrics. This resulted in the NVMe over fabric specification. With the NVMe over fabric specification done and having achieved adoption, our focus is now shifting to two areas. The first area is on leveraging the unique capabilities of NVM to enable new storage innovations, such as new command sets and various spec enhancements. The second area is on leveraging NVMe into new use cases, such as automotive, warehouse scale storage, and computational storage. As we expand into these new areas, a challenge emerged. How do we maintain stable specifications for mature volume applications while still enabling the rapid innovation that NVMe is known for? As a result of this, we decided to refactor the NVMe specifications. So the big thing in NVMe 2.0 is specification refactoring. A lot of people may expect that NVMe 2.0 means some major new feature. And while we have many new features in NVMe 2.0 that I'll describe later, the big change is a complete restructuring in a way that the NVMe specifications are organized. We did this for three reasons. The first is that we wanted to simplify development of NVMe-based technology. So for example, if you're designing an NVMe over Fabric storage device, you now don't need to comb through a bunch of PCIe transport spec information to determine what you need to do. The second reason is that we wanted to enable rapid innovation while minimizing the impact of broadly deployed solutions. To enable innovation, we understand that some of the new things that we may standardize may not gain widespread adoption. So refactoring the specifications allows us to contain these innovations in their own specifications. If they don't gain adoption, then they're simply specifications that no one reads, and we're not complicating the specifications for mature volume applications that people rely on. This allows us to take more risk in innovation. Finally, refactoring allows us to create a more maintainable structure where we are only updating the specifications that need to be updated. So for example, if we need to make an enhancement for PCIe SSDs, we can contain it to the PCIe transport specification. This slide shows the restructuring of the specifications. We took the NVMe Base specification and we broke it into three pieces. The base specification, which only describes the base NVMe architecture and command set, an NVM command set specification, which describes the I/O command set for block storage, and the PCIe transport specification, which describes all things related to PCIe. We also took the NVMe over Fabric spec and we moved architectural components into the NVMe Base specification and broke out the individual transports into their own specifications. So there's no longer an NVMe over Fabric specification. The NVMe Management Interface was largely self-contained, and while we moved a few minor architectural elements around, it remains largely unchanged. This slide shows the NVMe 2.0 family of specifications. We have the base specification. We have a collection of command set specifications. The NVM command set is what people think of when they think of NVMe, and it describes traditional block storage. We also have two new command sets, which I'll briefly describe later, the Zoned Namespaces command set and the key value command set. We also have a collection of transport specifications. We have the NVMe over PCIe transport specification, the NVMe over RDMA transport specification, and the NVMe over TCP transport specification. The NVMe over fiber channel transport is defined by T11 and not by the NVMe organization, so it's not listed here. So to summarize, NVMe 2.0 is all about refactoring the NVMe specifications, and the new NVMe 2.0 family of specifications are shown here. With that introduction to NVMe 2.0 spec refactoring, let's turn our attention to what is technically new in NVMe 2.0. The first big thing that we did in NVMe 2.0 was redefine how multiple I/O command sets are handled in NVMe. NVMe had support for multiple command sets from the beginning. NVMe 1.0 had support for 4 I/O command sets, although there was only one command set defined, the NVM command set. If you notice, the controller capabilities register has support for 4 I/O command sets, but the controller configuration register has a 3-bit field, which allows 8 command sets to be selected. 0 selects the NVM command set. We didn't like this inconsistency, so in NVMe 1.1, we added support for 8 command sets, although again, only one was defined, the NVM command set. Things stayed that way for a while, and then in NVMe 1.4, we introduced the administrative controller that can be used for management. Since an administrative controller doesn't support any command sets, we took the top encoding of the cap.css field to indicate that only the admin command set was supported, or alternatively, no I/O command sets were supported. This reduced the number of allowed I/O command sets to 7. Again, up to this point, the only I/O command set that we had was the NVM command set. It's important to note that while we had the foundation for multiple command sets from the beginning in NVMe, we were missing a lot of the key pieces required to actually implement multiple command sets. In NVMe 2.0, we defined a new mechanism for supporting up to 64 I/O command sets, defined all of the pieces necessary to actually support multiple command sets, and defined two new command sets, the Zoned Namespaces command set and the key value command set. Let's take a look at the new command set mechanism in a bit more detail. Associated with each namespace is now a command set. An NVM subsystem may support namespaces associated with different command sets at the same time, and you can mix and match attaching them to controllers in an arbitrary manner. On this slide, we have an NVM subsystem with 4 controllers and 9 namespaces. 4 of the namespaces support command set number 1, shown in green. 4 of the namespaces support command set number 2, shown in blue. And 1 namespace supports command set number 3, shown in purple. As this figure shows, you can have a controller that has all namespaces associated with 1 command set, which effectively means that controller can only use that 1 command set at that point in time. This is true for controllers 0 and 1 on this slide. Controller 0 only supports command set number 2, and controller 1 only supports command set number 1. Or you can have a controller that has namespaces attached associated with different command sets. This is true for controllers 2 and 3. When this occurs, the host can issue commands from different command sets that target these namespaces, and the commands can be interleaved in an arbitrary manner. So there's no notion of a controller being in a command set mode. You can issue a command from command set number 1 to one namespace, and immediately follow it by a command associated with command set number 2 to another namespace. If you're building an NVM subsystem, you may want to support multiple command sets, but you may not want to allow multiple command sets at the same time associated with a controller with commands being interleaved in an arbitrary manner. Since your use case may not require this, and supporting arbitrary interleaving increases implementation and validation complexity, you may want to prohibit this. To allow this, we added a restriction using the identify IO command set data structure that contains multiple command set combinations. Each command set combination is a bit vector with a bit per command set, which allows you to select a subset of command sets that may be enabled by a controller at a point in time. This restricts the interleaving of command sets associated with different command sets by the host. Using the IO command set profile feature, the host selects the command set combination that it wants to enable on a controller. So this allows you to control implementation complexity. It allows you to do things like the following. At one extreme, you can say, I want to support IO command sets 1, 2, and 3 on my controller, but I only want to have 1 enabled at a time. At the other extreme, you can say, I want to support all 3 command sets enabled at the same time, and with commands interleaved in an arbitrary manner. You can also do things in between. For example, you can express that you want to allow command sets 1 and 3 at the same time, or you can enable command set 2, but you can't enable all 3 command sets at the same time. This slide shows how a command set is selected when you have a controller that is enabled for simultaneously supporting multiple command sets. Recall that each namespace is associated with exactly 1 command set. So the way it works is that when a controller decodes a command, it takes the namespace identifier field that selects the namespace operated on by that command and determines the command set with which that namespace is associated. Now that it knows the command set on which the command is operating as determined by the namespace, it uses that information to parse the actual command. With that introduction to multiple command sets, let's take a look at the 2 new command sets that we've defined. The first new command set is the Zoned Namespaces command set. It's similar in structure to what is done in other storage architectures for SMR drives, but is optimized for NVM, such as NAND. Logical blocks are grouped into zone, and the logical blocks of a zone must be written sequentially. There's a state machine associated with each zone, and in order to read or write logical blocks in a zone, the zone needs to be in a particular state. State transitions may be triggered explicitly by a host or implicitly as a result of a host action. There are 3 benefits of the sequential writes in the Zoned Namespace command set. The first is that they reduce write amplification. The second is that they reduce the amount of required over provisioning. Finally, sequential writes reduce the size of the mapping table required over what is required for normal NAND FTL associated with the NVM command set. The second new command set is the key value command set. This command set is optimized for unstructured data. Instead of reading and writing logical blocks, the host can access data using a key value pair. You can think of the key as an identifier for an object and the value as the data for an object. A key can be 1 to 16 bytes in size, and the value can be 0 to 4 gigabytes in size. With this command set, you don't read and write data, you retrieve a key value and you store a key value. So it's very different from the NVM command set we have today. So with this brief introduction to the new NVM command sets, let's move on to some other new features in NVMe 2.0. When many of you think of NVMe, you think of a PCIe SSD. However, the NVMe architecture is now the new language of storage and is being used to construct warehouse-scale storage systems. Many of these warehouse-scale storage systems are represented by a single NVM subsystem. Up to this point, an NVM subsystem was a monolithic thing with a controller and namespaces. In an NVMe SSD, it's typically implemented by an ASIC with some NAND. In a warehouse-scale storage system, it could consist of many refrigerator-sized racks. These racks fail and need to be replaced. Sometimes racks need to be added to expand capacity. In other cases, firmware associated with the rack needs to be updated. What we've done in NVMe 2.0 is define how an NVM subsystem may be partitioned into multiple domains. Domains are a new architectural element in the NVMe architecture. A domain may contain control capacity, controllers, ports, and communicate with other domains. In the NVMe 2.0 base specification, we define how domains may be added, removed, reconfigured, or partitioned. This includes things like how reservations are handled when an NVM subsystem that was partitioned is unified. We also define how an NVM subsystem signals a domain change to a host. Another new feature in NVMe 2.0 is the addition of a copy command to the NVM and Zoned Namespaces I/O command sets. This command is pretty simple. It allows you to copy one or more non-contiguous LBA ranges to a contiguous LBA range in the same namespace without transferring data through the host. This operation is useful for things like host-based FTLs. So before this command, in order to perform a copy, the host had to read data into host memory with an IO read command, and then write data back to a namespace using an IO write command. The new copy command allows you to do that in one operation without transferring data through the host. This saves host memory bandwidth, interconnect bandwidth, and reduces latency. Next, we have command group control. We added a new lockdown admin command to NVMe that may be used to prohibit the execution of a command or modification of a feature. The lockdown command can be used to prohibit execution of an admin command, a set feature command that modifies a specific feature identifier, or an NVMe Management Interface command. With the lockdown command, one can also control the interface on which the command is prohibited. The command could be prohibited in-band on an admin queue, out-of-band through a management interface, or both in-band and out-of-band. When a command is locked down or prohibited, it is prohibited until the next power cycle or explicitly re-enabled using the lockdown command. Another new feature in NVMe 2.0 are enhancements in the way protection information works. Since we wanted NVMe to be used across storage applications and protection information was required in many enterprise applications, we supported protection information from the beginning in NVMe 1.0. To maintain compatibility with other storage architectures, we use the same format as protection information in T10. As shown in the upper left of this slide, there's a 16-bit guard, a 16-bit application tag, and a 32-bit reference tag. Since a 16-bit guard is viewed as insufficient for large logical blocks, the first change we made in NVMe 2.0 to protection information was to add support for the 32-bit guard and a 64-bit guard. You can see the format of the 32-bit guard protection information in the middle and the 64-bit guard on the right. The second change that we made was to add support for a storage tag in addition to a reference tag. The storage tag is an opaque data field not interpreted by the controller. During protection information checking, the value of the storage tag is compared to a value provided in the command. Since the use and size of the storage tag and reference tag varied per application, we added a storage and reference space field in the protection information so that one could configure how many bits one wanted to allocate for this from this field for the storage tag and how many bits one wanted to allocate for a reference tag. Some applications may want a large reference tag, other applications may want a large storage tag, yet other applications may want to split this field into a storage and reference tag. The figure in the lower middle of this slide shows how this works. When you split the storage and reference space field, the upper bits become the storage tag and the lower bits become the reference tag. In NVMe 1.4, we added endurance groups and media units as architectural elements to the NVMe architecture. Before NVMe 1.4, we had namespaces that could be used in an NVM set. In NVMe 1.4, we allowed NVM sets to be in an endurance group. An endurance group is a portion of NVM in an NVM subsystem whose endurance can be managed as a collection. In NVMe 1.4, we also added media units that can be used to construct endurance group. A media unit represents a component of the underlying media in an NVM subsystem. All this was great, but we didn't have a mechanism to configure any of this. The idea was that it came pre-configured from the factory. This is common in the way we do things in NVMe. We start simple and then we add things as things are needed. What we added in NVMe 2.0 was the ability to configure all this. We added a new capacity management command to the admin command set. And with this command, you can create and delete NVM sets, create and delete endurance groups, allocate media units to an endurance group, and allocate media units to NVM sets. Turning our attention to Fabric, NVMe 2.0 adds new NVMe over Fabric security features. NVMe over TCP previously supported Transport Layer Security, or TLS, version 1.2. TLS 1.2 was released in 2008 and was considered fairly secure, but vulnerabilities have been discovered that call the security of TLS 1.2 into question. For this reason, we're moving NVMe to TLS 1.3. Starting with NVMe 2.0, all NVMe over TCP implementations that implement TLS are now required to support TLS 1.3. NVMe 2.0 still allows TLS 1.2 as legacy, but everyone is strongly encouraged to move to TLS 1.3. Another security feature that we added was mutual host and NVM subsystem in-band authentication using a Diffie-Hellman HMAC CHAP protocol. This allows a host and an NVM subsystem to authenticate each other and make sure they're actually talking to who they think they're talking to. The final major addition to NVMe 2.0 that I'm going to describe is support for rotational media such as hard drives. I never thought I would see this day, but as NVMe has become the new language of storage, people are architecting their systems around NVMe natively and want to be able to plug in hard drives into these systems. So we added support for hard drives to NVMe 2.0. Enhancements for rotational media include an indication that an endurance group and associated namespace store data on rotational media, a log page that describes rotational media. It includes things such as the number of actuators, rotational speed, and so on. Finally, since spinning up a hard drive can consume a lot of power, we added spin-up control. In summary, NVMe has become the new language of storage and is now being used in everything from mobile devices and simple PCIe SSDs to warehouse-scale storage arrays. We now support every major transport and are shifting our focus to new innovations enabled by NVM and new use cases. The NVMe 2.0 specifications are all about refactoring. We refactored the specifications to ease development of NVMe-based technology, enable rapid innovation by minimizing change to specifications associated with broadly deployed solutions, and creating an extensible specification structure that will allow the next phase of growth for NVMe. The NVMe technical community continues to accelerate technical development by maintaining and extending existing specifications, while at the same time delivering new innovations. In this presentation, I've given you an overview of NVMe 2.0. I encourage you to go to the NVM Express website and download the specifications for more details. Thank you.